Good morning. We need to evaluate this integral, right? And the integrand is involving the cosine function. For these kind of integrals, we always take z equal to e the power iota theta. And then we get dz and then find cos theta or sin theta in terms of z. So before starting with the solution, let's read some remarks. Number 1. Whenever you are having the integrand of the kind or the function involving cosine and sine theta, then put z equal to e the power iota theta. Then you get dz to be iota e the power iota theta d theta. This will be changed into iota e the power iota theta is z. So this is iota z. So we find d theta to be equal to dz divided by iota z, right? Second, we know that cos theta is e the power iota theta plus e the power minus iota theta divided by 2. So this can be further written as this is your z. So writing this as z plus this is z inverse. So we write this as 1 by z and taking 1 by 2 outside of this bracket. So we have cos theta to be equal to 1 by 2 into z plus 1 by z. Similarly, we can get sin theta to be equal to 1 divided by 2 iota into z plus 1 by z. Please remember, for sin theta, we have to multiply this 2 with iota, right? Then third, as theta varies from 0 to 2 pi, here the theta is varying from 0 to 2 pi, which means z moves around the unit circle mod z equal to 1 in anti-clockwise direction. We take the circle to be the unit circle, right, for this. Now let's start with the solution. So this is the given integral. So for this, we have to put z equal to e the power iota theta. Then we get dz to be equal to e the power iota theta into iota d theta. That is iota z d theta. So we get the value of d theta to be dz divided by iota z. So now this integral can be written as, instead of d theta we write dz divided by iota z into 2 plus cos theta. That is 2 plus, cos theta is z plus 1 by z into 1 by 2. And the integral is around the circle, the unit circle mod z equal to 1. It is the unit circle mod z equal to 1. Is it okay? Fine. Alright. We need to solve this denominator. So this is equal to, 1 divided by iota z dz divided by, from here we get, this is 2 plus 1 by 2 into z square plus 1 divided by z. Further, when taking the LCM, we get 4z plus z square plus 1 divided by 2z. So I am taking this 2z in the numerator further. So writing here 2z, and in the denominator we have z square plus 4z plus 1. Is it okay? Fine. Okay. So this z is cancelled out with this and we get 2 divided by iota outside of this integral, and inside we have dz divided by z square plus 4z plus 1. And now we need to find the poles by taking this denominator to be equal to 0. So when taking the denominator to be equal to 0, we get the value of z to be minus 4 plus minus square root of 16 minus 4 divided by 2. So that is equal to minus 4 plus minus square root of 12 divided by 2. Square root of 12 is 2 root 3, which further becomes, if we take 2 common from the numerator and denominator, we get minus 2 plus minus root 3. So this is minus 2 plus minus root 3. So these are the 2 points we are getting. Now we need to check which of these points lies inside the circle mod z equal to 1. Which of the point lies inside the circle? We are having z equal to minus 2 plus root 3 and minus 2 minus root 3. So from these 2 points, only minus 2 plus root 3 lies inside the circle, and this point does not lies inside this circle. So we need to find the residue for this point only, right? So let's write this. Of the 2 poles, only z equal to minus 2 plus root 3 lies inside the unit circle mod z equal to 1. So now calculating the residue at z equal to minus 2 plus root 3. Let me take this as alpha. So what is the formula for that? It is limit z tending to alpha, z minus alpha into fz. And what is your fz? From here we take fz to be equal to 1 divided by the denominator z square plus 4z plus 1. So writing fz to be 1 divided by z square plus 4z plus 1. When we put z equal to alpha, we get 0 in the numerator and also 0 in the denominator. So this is the 0 by 0 format, right? So now applying the L'Hopital's rule over here, let's find the derivative of the numerator with respect to z. That is 1 divided by derivating the denominator with respect to z. That is 2z plus 4. And now putting the value of z as alpha over here, we get this to be 1 divided by 2 into alpha plus 4, where alpha is what? It is minus 2 plus root 3. For the simplicity, we have taken this value to be alpha. So this is 1 divided by 2 into minus 2 plus root 3 plus 4. So that gives, okay, this is minus 4 plus 2 root 3 plus 4. These two cancelled out and we get the residue to be 1 divided by 2 root 3. Right? And now by residue theorem, the given integral, that is dz divided by z square plus 4z plus 1. So this is equal to 2 pi iota into what is the residue? 1 divided by 2 root 3, right? So writing here 1 divided by 2 root 3. So just cancelling this 2 from this and we get pi iota divided by root 3. The integral is from 0 to 2 pi d theta divided by 2 plus cos theta, right? So we have written this integral to be equal to 2 divided by iota into the integration over the circle C dz divided by z square plus 4z plus 1. Please remember, please note that when we have substituted z equal to e the power iota theta over here, this integral is changed into this integral, and this integral is multiplied with 2 divided by iota also, right? So solving this further, so this is 2 divided by iota. Okay, what is the value for this integral? We have calculated this to be pi iota by root 3. So this is pi iota by root 3. So this iota is cancelled out with this and we get the final answer to be 2 pi divided by root 3. So this is how we solve these kind of integrals involving the cosine or sine functions, where we need to first take z equal to e the power iota and then continue further. Okay, thank you. Stay blessed.